Welcome back to the lecture videos for section 8.4. I hope that after that last video that you took a break, got a cup of coffee, or went for a walk, something like that, because it was a lot of information. Note that in this section we are not learning anything new. We're going to practice trigonometric substitution under a couple of specific applications. The first one is finding the area under a curve. Example 2 says find the area between y equals 1 over the square root of x squared plus 16 on the closed interval from 0 to 3. Now, if you graph this in your calculator, just so we can kind of get a visual of what it is that we're doing, the curve is going to look something like this. You can set your viewing window something like x equals negative 10 to 10. Give a small window for y, something like 0 to 1. And then the curve does something like this. So the closed interval that we're working on is from 0 to 3. Which means the area that we're looking at from x equals 0 to x equals 3 would be this shaded region right here. Now we don't have a Euclidean formula to find the area of such an irregularly shaped region, but we can apply calculus to find the area of any region that we can describe with functions. So the way that we'll calculate this area is by using a definite integral from x equals 0 to x equals 3 of the function 1 over the square root of x squared plus 16 dx. So observe that if the radical were not there, if it was just 1 over x squared plus 16, we could integrate it directly and get an arctangent. But because we have the presence of that radical, and we can't do an ordinary u substitution, we will use trigonometric substitution. Since we have the sum of two squares in the denominator, then the trig substitution that we're going to use is x equals 4 tangent of theta. Now remember, the 4 comes from the square root of this constant right here. Then dx would be 4 secant squared theta d theta. So we want to rewrite our integral now in terms of theta. Keep in mind, I'm changing variables from x to theta, so the limits of integration 0 and 3 are x values only, and they cannot be used with theta. So let's go ahead and rewrite the integral in terms of theta, and then we'll go ahead also and update our limits of integration. So in the denominator, we have 1 over the square root of x squared plus 16. X is 4 tangent of theta, so x squared would be 16 tangent squared theta, and then we have our plus 16. Now remember, don't forget about the dx term. As you're learning trigonometric substitution, that term is easy to overlook. We are going to replace that with 4 secant squared theta d theta. Now at this time, let's go ahead and update our limits of integration since we are dealing with a definite integral. The relationship between x and theta is given by our substitution statement right here. So working on our lower limit of integration, which is an x value, we can plug 0 in for x and use that to calculate the corresponding theta. If I divide both sides by 4, we need a value, an exact radian value from the unit circle where tangent is equal to 0. And of course, tangent is equal to 0 when theta is equal to 0. So my new lower limit of integration is going to be 0. Working on our upper limit of integration, when x is 3, we need to find the corresponding tangent or theta value. So let's go ahead and divide both sides by 4. So tangent of theta is equal to 3/4. Now thinking about our unit circle, 3/4 of course is not a unit circle value, so I'm not going to be able to solve for this exactly, so we'll do it symbolically. Theta then is inverse tangent of 3/4. So my upper limit of integration is inverse tangent, you can also write arctangent, of 3/4. Now that those have been knocked out, let's go ahead and work on our integral. So we have the integral from 0 to inverse tangent of 3/4. In the denominator here, under that radical, we can factor out the greatest common factor of 16, and that's going to leave behind tangent squared theta plus 1. And we still have this factor, 4 secant squared theta d theta. When we split the radical over each factor, well, before we do that, let's apply our Pythagorean identity. and recognize that tangent squared of theta plus 1 is secant squared of theta. Then we'll be able to evaluate that radical. So splitting the radical up, the square root of 16 is 4. The square root of secant squared, of course, is secant theta. And this is going to simplify nicely. So we can see that not only do the 4's cancel, but one of the secant factors cancels. So the problem that we need to execute becomes the integral from 0 to inverse tangent of 3/4 of little old secant of theta d theta. At this point, we do have to remember how to integrate secant of theta. We're going to get the natural log of the absolute value of secant of theta plus tangent of theta. Now, remember, we're working in a definite integral, so the plus c is not necessary. We need to evaluate this from 0 to inverse tangent of 3/4. Plugging in our upper limit of integration, we have the natural log of the absolute value of secant of inverse tangent of 3/4 plus tangent of inverse tangent of 3/4. That one won't be so bad to evaluate. There's our upper limit minus the lower limit, which is natural log of the absolute value of secant of 0 plus tangent of 0. Now I'm going to look at the easy part first, looking at the antiderivative evaluated at the lower limit of integration. Secant of 0, think 1 over cosine of 0, that's equal to 1, and tangent of 0, of course, is 0. So here we need to evaluate negative natural log of 1. Well, natural log of 1 is 0, so our entire lower limit zeroes out. Now that that's out of the way, we can focus on the upper limit. Notice we have secant of inverse tangent of 3/4, and then tangent of inverse tangent of 3/4. We can evaluate this exactly if we use our right triangle relationships. And I'm just going to come over here to the left where I have some space and recognize that inverse tangent of 3/4 is some angle theta. And if I take the tangent of both sides, we can see tangent of theta is equal to 3/4. So if we assume that theta is an angle on a right triangle and tangent is opposite over adjacent, then the opposite side would be 3 and the adjacent side would be 4. If we solve for the hypotenuse of this triangle using Pythagorean theorem, we would end up with 5. So we need to find secant of this angle. Secant, of course, is 1 over cosine. Cosine is adjacent over hypotenuse. So we can see that cosine of this angle, represented by inverse tangent of 3/4, is adjacent over hypotenuse. That means secant is 5 over 4. So back to our evaluation over here, we have natural log of the absolute value of secant of inverse tangent of 3/4. We figured out that was 5/4. And the next term's a little easier. Tangent of inverse tangent of 3/4. Tangent and inverse tangent are inverse functions, so you don't get anywhere when you apply two inverse functions successively. So we have natural log of 5/4 plus 3/4. Or we could say altogether natural log of the absolute value of 8 over 4. 8 over 4, of course, reduces to 2. And because 2 is positive, the absolute value bars are not necessary, so we can drop those. And remember, we were calculating an area, so I am going to say here u squared for units squared. So the area of the red shaded region on our graph is exactly natural log of 2 units squared. But if we want to know what does that mean, we could approximate natural log of 2 with our calculator. It's about 0.7 square units. So in that problem, we were using a definite integral to model the area between the curve and the x-axis, but it actually took trigonometric substitution to evaluate that definite integral. Now let's consider another application which requires trigonometric substitution. Part B will look at arc length. The length of an arc on the curve y equals f of x over the closed interval from a to b is given by the integral from a to b of the square root of 1 plus f prime of x squared dx. Now, you may have never seen this formula before. This is derived in your book. We're not going to take the time to derive it here, but it's an extremely useful formula that allows us to measure the linear distance on a curve from between two x values. So let's see how this works in example 3. Find the exact length of y equals x squared on the closed interval from 0 to 1/2. To get a visual of what we're calculating, I am going to go ahead and sketch that parabola. This is your fundamental parabola, y equals x squared. So the curve looks approximately something like this. So our goal is to find the actual length of the curve from y equals 0 to y equals 1/2. Of course, this is not drawn to scale. So we're going to use this integral to measure the linear distance of that particular part of the curve. So following this given formula, we're going to set this up as the integral from x equals 0 to x equals 1/2 of the square root of 1 plus, now notice we have f prime of x squared. If f of x is equal to x squared, then f prime of x is equal to 2x. So we're going to find 1 plus the quantity 2x squared dx. Notice for this integral that we have the pattern of the sum of two squares under a radical. So hopefully you're becoming sensitive to these types of patterns. This is a problem that's going to require trigonometric substitution. And because we're dealing with the sum of two squares, we're going to use the tangent function. So we're going to let 2x equal tangent of theta. Now, where did that come from? Well, I'm looking at that first constant and viewing it as the square of 1, and the second constant we have u squared. So when we have the sum of two squares, we let u equal a tangent theta, where a, of course, is the square root of the constant. But in this case, u is a function of x. U is equal to 2x. So we let 2x equal tangent of theta. Then we'll proceed at this point as we normally do to differentiate both sides. The derivative of tangent of theta is secant squared theta d theta. Observing that what's left over in the integral here is just dx, I'm going to isolate dx by multiplying both sides by 1/2. Then we're ready to rewrite our definite integral in terms of theta. Now for now, I'm going to hold off on the limits of integration and work on the integrand and the differential term. We have 1 plus the quantity 2x squared, and we know 2x represents tangent. So 2x quantity squared is tangent squared. And we're going to replace the dx term with 1/2 secant squared theta d theta. Now this would also be a good time to update our limits of integration. So my lower limit of integration is 0, and I'm going to use this relationship to go from an x value to a theta value. So if x is 0 and I plug 0 in here, we can solve this little equation for theta. If tangent of theta equals 0, then theta equals 0. So my new lower limit of integration is also going to be 0. Looking at our second or our upper limit of integration, we're going to plug 1/2 in for x. We have 2 times 1/2 equals tangent of theta. So we need the angle on the unit circle in radians where tangent is equal to 1, and that angle would be pi over 4. So our upper limit in this case will be pi over 4. Next, we can proceed with simplifying our integrand. We have the integral from 0 to pi over 4. Notice under the radical we have 1 plus tangent squared of theta. If we apply our Pythagorean identity, that's the same thing as secant squared of theta. We've got a factor of 1/2. We can move that out of the way in front of the integral, and we still have secant squared theta d theta. Now, the square root of secant squared of theta is secant of theta, and secant times secant squared is none other than our friend secant cubed of theta. I think it's so interesting how often this integral pops up, integral of secant cubed. It shows up in this seemingly very simple problem to find the length of a fundamental curve on a small interval on the x-axis. So once again, I'm not going to go through the details of integrating secant cubed. We did that in great detail on a previous video using integration by parts. I'm just going to use the results of what we came up with. If you'll remember, the integral of secant cubed became 1/2 times secant of theta tangent of theta plus 1/2 times the natural log of the absolute value of secant of theta plus tangent of theta. Again, those are results from a previous video. Now, this is a definite integral, so we're going to need to evaluate this from 0 to pi over 4. So I'm going to do two things. I want to distribute this 1/2 at the same time as plugging in our upper and lower limits. So our new coefficients will both be 1/4. So plugging in our upper limit, we have 1/4 times secant of pi over 4 tangent of pi over 4 plus 1/4 natural log of the absolute value of secant pi over 4 plus tangent pi over 4. So that is our upper limit plugged in. Now we're going to subtract our lower limit plugged in. So plugging 0 in, we have 1/4 secant 0 tangent 0 plus 1/4 natural log of the absolute value of secant of 0 plus tangent of 0. And that is our lower limit. Now, just as a little bit of side work here, let's make some observations. Secant of pi over 4 is 1 over cosine of pi over 4, right? Cosine of pi over 4 from our unit circle is square root of 2 over 2. And if we have 1 divided by a fraction, that's the same thing as 1 times the reciprocal. And if we rationalize, because this will simplify, we would end up with 2 square root of 2 over 2 or square root of 2. So secant of pi over 4 equals square root of 2. So working on my evaluation, we have 1/4 times secant of pi over 4, which is the square root of 2, and tangent of pi over 4, that's an easy one, that's equal to 1. Then we have plus 1/4 times the natural log of the absolute value of secant of pi over 4, that's square root of 2, plus tangent of pi over 4, which is 1. Now, being careful to subtract both terms of our lower limit, we're going to subtract 1/4 secant of 0. Secant of 0 is 1 over cosine of 0. Cosine of 0 is 1, so its reciprocal is also 1. Tangent of 0 is 0, so that whole term is going to 0 out. Now be careful here, we're subtracting both terms from our lower limit here, so I'm going to distribute this negative to both of these terms here. So we have minus 1/4 natural log of the absolute value of secant of 0, which is 1, plus tangent of 0, which is 0. So cleaning up our solution a little bit here, we have the square root of 2 over 4 plus 1/4 times the natural log. Absolute values are not necessary because we have a positive argument, so we can demote those. This term goes to 0, and our last term is natural log of 1, also equal to 0. So the exact value of the length of that simple curve from x equals 0 to x equals 1/2 is this number, square root of 2 over 4 plus 1/4 natural log square root of 2 plus 1. And this is a linear measure. We're talking about linear units or units to the first power. So we've looked at an example of where we can use a definite integral to calculate a two-dimensional area. And in this case, we're using a definite integral to measure a one-dimensional length. So integrals are very versatile. When you get to Calculus 3, you're going to have the opportunity to progress from two-dimensional mathematics, that is working in the plane, to working in 3 space, also known as R3 or three-dimensional space. You'll be working with 3 axes at right angles to each other. And instead of finding the length of a curve in the plane, you may end up finding the length of a space curve or something like this. So a one-dimensional path through three-dimensional space. You will apply integration with a little bit of a different process to accomplish the same thing in three-dimensional space. So that's pretty interesting. Another thing you'll have the opportunity to do in Calculus 3, which is kind of related to what we're doing here, is instead of finding the area under a curve and the x-axis, you'll be finding the volume between a surface and the xy plane. So instead of a parabola, you'll be working with a paraboloid or something that looks like this, kind of like a parabolic shell, and you'll be able to find the volume between that parabolic shell and the xy plane. And you can use a double integral to do that. You can use a triple integral. So you'll be working problems that look something like this, for example. So the point is simply that the skills that you are developing in Calculus 2 with integration will transfer to more realistic problems, problems working in three-dimensional space, and the integration skills that you're learning here for single integrals will be absolutely necessary to work something like this with the triple integral. So it pays to really sit down and master these skills now. And one of these days, you'll look back on learning trigonometric substitution in Calculus 2 and you'll say, oh, those were the good old days. So thanks for listening. Hope you have a good day.